330 million light-years across, and almost nothing there, just darkness folded into more darkness, a sphere of absence so vast that light itself seems to lose its way. The Boötes Void sits in the northern sky like a held breath, a place where the universe chose emptiness over stars, where galaxies that should number in the thousands dwindle to perhaps 60, scattered and faint and impossibly alone. There is something strangely comforting in such immensity, in knowing that even the cosmos holds quiet places, rooms without furniture, spaces given over to stillness. If these slow journeys through the dark bring rest, a subscription means more will arrive when needed. For now, though, there is only this, a void, a mystery, a gentle falling away from everything bright, and the story can begin here, in the quiet between the stars. In the quiet hours of the night, when most of the world has settled into sleep, there have always been those who remain awake, peering upward into the darkness with careful instruments and patient attention. During the 1970s and 80s, a generation of astronomers began a project of extraordinary ambition and equally extraordinary tedium, the sort of work that requires years of dedication and produces results only gradually, like a photograph developing in the slowest possible darkroom. They set out to map the positions of galaxies not merely across the sky, as earlier surveys had done, but in 3 dimensions, reaching outward into the depths of space itself, and in doing so they would discover that the universe possesses a structure far more intricate and far more peculiar than anyone had previously imagined. The challenge they faced was one of measurement, for while it is relatively straightforward to note where a galaxy appears on the dome of the sky, determining how far away it actually lies requires considerably more effort. A faint galaxy might be a small one relatively nearby, or it might be an enormous one at a tremendous distance, and the human eye cannot distinguish between these possibilities simply by looking. The solution to this problem had been developing for decades, building upon work that stretches back to the early 20th century, and it relies upon a phenomenon that occurs when objects in space are moving away from us, a gentle stretching of the light they emit that shifts their colors toward the red end of the spectrum, like the way a sound drops in pitch as its source recedes. This stretching of light, known as redshift, provides astronomers with a remarkably useful tool, for in an expanding universe, the farther away a galaxy is, the faster it appears to be receding from us, and therefore the more its light is shifted toward the red. By carefully measuring the precise wavelengths of light from a galaxy and comparing them to the wavelengths that same light would have if the galaxy were stationary, astronomers can calculate how quickly the galaxy is moving away, and from that speed they can estimate its distance. The process requires obtaining a spectrum of each galaxy, spreading its light out into its component colors and measuring the positions of specific features within that spectrum. And in the era before digital detectors and automated systems, this was painstaking work indeed, requiring long exposures and careful analysis for each individual galaxy. In the 1960s, before the great redshift surveys began in earnest, there were already hints that galaxies might not be distributed randomly throughout space. At Lick Observatory in California, astronomers had undertaken the laborious task of counting galaxies in different parts of the sky, examining photographic plates and tallying up the numbers of galaxies visible in various directions. This work, though it could not measure distances directly, revealed that galaxies seemed to cluster together in some regions while being notably sparse in others, suggesting that the universe might possess some kind of large-scale structure rather than being a uniform scattering of island universes. The patterns were tantalizing but difficult to interpret, like looking at the shadows cast by a mobile and trying to deduce the shapes of the objects hanging from it. The breakthrough that would transform our understanding of the cosmos began in earnest in 1977, when Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics initiated what would become known as the CFA Redshift Survey. Their approach was methodical and unglamorous, the sort of science that does not make headlines while it is being conducted but rather accumulates its significance slowly over years of consistent effort. They selected regions of the sky and set about measuring the redshifts of every galaxy within those regions above a certain brightness, building up their map one galaxy at a time, each measurement requiring its own telescope observation and its own careful spectral analysis. The work proceeded at a pace that might seem glacial by the standards of our current age, when computers can process thousands of objects in a single night. Geller and Huchra and their collaborators would observe galaxies whenever the weather and the telescope schedule permitted, recording the spectra on photographic plates initially and later on electronic detectors as the technology improved. Each spectrum had to be examined and measured, the redshift calculated, the result added to the growing database. It was the astronomical equivalent of surveying a vast wilderness one tree at a time, marking each position on an ever-expanding map, and it required the particular combination of patience and curiosity that characterizes so much of scientific work. As the years passed and the number of measured galaxies grew from hundreds into thousands, a picture began to emerge that surprised even those who had expected to find some kind of structure. The galaxies were not scattered randomly, nor were they simply clumped into clusters with empty space between them. Instead, they seemed to be arranged along filaments and walls, like the threads of an impossibly vast spider web or the surfaces of soap bubbles floating in infinite darkness. Between these structures lay regions where galaxies were notably absent, empty spaces that the astronomers began to call voids, and the overall impression was of a universe whose matter had organized itself into a kind of cosmic foam or sponge. This pattern, which came to be known as the cosmic web, represents one of the most fundamental features of the universe we inhabit, and yet it had remained hidden until astronomers developed the tools and the patience to reveal it. The filaments are rivers of galaxies, stretching across millions of light-years, while the walls are vast sheets of galaxies that seem almost flat when viewed edge-on. Where filaments and walls intersect, galaxy clusters form, the dense knots in the cosmic web where gravity has drawn matter together most strongly. And everywhere between these structures, the voids persist, regions where galaxies are rare or absent entirely, like the empty spaces within a loaf of bread or the air pockets within foam. By the late 1980s, the CFA survey had accumulated enough data to produce maps of startling clarity and unexpected revelation. In 1989, Geller and Huchra announced the discovery of what they called the Great Wall, an enormous sheet of galaxies stretching across more than 500 million light-years, so large that light takes 500 million years to travel from one end to the other. This structure seemed almost impossibly vast, challenging assumptions about how much time the universe had had to assemble such enormous features. And yet there it was, plainly visible in the data, a wall of galaxies like nothing anyone had predicted. The Great Wall was not unique, but rather the largest and most prominent example of the structures that the survey was revealing everywhere it looked. The cosmic web seemed to permeate all of space, at least everywhere the astronomers had measured, suggesting that this pattern of filaments and walls and voids was a universal feature of our cosmos rather than a local peculiarity. The universe, it seemed, was not a simple collection of objects but a structured environment, an architecture of matter that had been shaped by gravity over billions of years into patterns of considerable complexity and subtle beauty. The typical voids that astronomers found in these early surveys were substantial but not extraordinary, spanning perhaps 30 to 50 million light-years across. These empty regions, while impressive in their scale, fit reasonably well with theoretical expectations about how the universe might have evolved from its initial nearly smooth state. Small fluctuations in the distribution of matter in the very early universe would have been amplified by gravity over cosmic time, with denser regions attracting more matter and becoming denser still, while less dense regions would have been gradually emptied as their contents were drawn toward neighboring concentrations. The resulting voids were the negative spaces left behind, the places from which matter had been evacuated. This picture of the cosmic web as something like Swiss cheese or soap bubbles proved useful for understanding both the observations and the theoretical models. In Swiss cheese, you have the cheese itself forming a connected structure surrounding bubbles of empty space, and in soap bubbles, you have thin films of soapy water enclosing pockets of air, with the bubbles sharing walls where they meet. The cosmic web is somewhat similar, with the filaments and walls of galaxies forming a connected structure that surrounds the empty voids, and the voids themselves sharing boundaries with their neighbors in a kind of cosmic tessellation. The astronomers who conducted these surveys developed a particular intimacy with the large-scale structure of the universe, an intimacy born of long hours at the telescope and longer hours analyzing data. They came to know the cosmic web not as an abstraction but as a familiar landscape, even though it was a landscape measured in millions of light-years rather than in miles or kilometers. They knew where the walls were and where the voids opened up, which clusters marked the intersections of filaments and which regions seemed unusually empty. The universe revealed itself to be a structured place, not random but organized according to principles that gravity had written into the distribution of matter over billions of years. What the astronomers expected, as they continued their surveys and extended them to cover larger and larger volumes of space, was to find more of the same pattern repeated throughout the observable universe. They expected to find more filaments and walls, more clusters and groups, and more voids of roughly the same size as those they had already discovered. The cosmic web seemed to possess a characteristic scale, a typical size for its features that was set by the physics of gravitational collapse and the expansion of the universe, and there was no particular reason to expect that scale to vary dramatically from one region of space to another. This expectation was entirely reasonable, based as it was on both theoretical understanding and observational experience. The universe, though structured, seemed comprehensible, a place where the patterns repeated themselves in ways that could be understood and predicted. The voids were empty spaces, yes, but they were empty spaces of a familiar sort, the natural consequence of matter flowing toward regions of higher density and leaving behind regions of lower density. They were part of the expected architecture of the cosmos, neither surprising nor disturbing, simply the negative space that gave the cosmic web its form. As the surveys extended outward, mapping ever more distant regions of the universe, the astronomers settled into a kind of comfortable familiarity with the structures they were finding. The work remained demanding, each new region requiring its own set of observations and its own careful measurements, but the overall pattern seemed established. The cosmic web was there, stretching in all directions, its filaments and walls and clusters and voids forming a framework that organized the visible matter of the universe into a comprehensible architecture. And yet, as with so many things in science, the comfortable familiarity would not last forever. The universe, it seems, had not finished revealing its surprises, and in one particular direction in the sky, in the constellation Boötes, the astronomers would eventually find something that did not fit the expected pattern at all, a void so vast and so empty that it would challenge their assumptions about what the cosmic web could be. But that discovery lay still in the future, and for now, the astronomers continued their work, mapping the positions of galaxies one by one, building up their picture of a structured but comprehensible universe, unaware of the extraordinary emptiness that awaited them. In the year 1981, at the University of Michigan in Ann Arbor, a team of astronomers was engaged in what might be described as one of the more methodical and quietly ambitious projects in observational cosmology at that time. The principal investigator was Robert Kirshner, a man whose career would eventually span decades of careful observation and who would later become known for his contributions to our understanding of supernovae and the accelerating expansion of the universe. Though at this particular moment in the early 1980s, he and his colleagues were occupied with a somewhat different question, one that concerned itself with the large-scale distribution of galaxies across the sky and what that distribution might tell us about the underlying structure of the cosmos itself. Working alongside Kirshner were three other astronomers whose names would become permanently associated with the discovery that was about to unfold, though none of them could have anticipated the peculiarity of what their data would eventually reveal. Augustus Imler Jr. was one of these collaborators, a researcher whose expertise in galaxy populations and clustering would prove essential to interpreting the strange absence they were about to encounter. Paul Schechter, another member of the team, had already made significant contributions to the study of galaxy luminosity functions, and his analytical approach would help confirm that what they were seeing was not an artifact of their methods but something genuinely present, or rather genuinely absent, in the actual universe. Stephen Schechtman rounded out the group, bringing his own observational skills to what was intended to be a straightforward survey of cosmic geography. The project itself was designed around a principle that had become standard in large-scale structure studies of that era, which involved selecting particular directions in the sky and then systematically cataloguing the galaxies that could be observed within cone-shaped survey volumes extending outward from our own position in space. One might imagine this technique as something like looking through a long, gently widening tube aimed at a specific patch of sky and counting every galaxy that falls within that tube out to various distances, measuring not only the angular positions of these objects but also their redshifts, which provide information about how far away each galaxy actually is. By repeating this process in multiple directions and comparing the results, astronomers could begin to build up a three-dimensional picture of how galaxies are distributed through space, whether they cluster together in certain regions, whether they form sheets or filaments, and whether there might be relatively empty regions between the denser concentrations. The particular direction that would prove so consequential for Kirshner and his team lay in the vicinity of the constellation Boötes, which is sometimes called the herdsman and which can be found in the northern sky, not far from the more easily recognized shape of the Big Dipper. The specific coordinates toward which they directed their attention were centered approximately at a right ascension of 14 hours and 50 minutes and a declination of positive 46 degrees, which places the survey field in a region of sky that appears relatively unremarkable to the casual observer. Just another patch of darkness dotted with the faint light of distant stars and the even fainter smudges of faraway galaxies that require telescopes to see at all. The methodology employed by the team was careful and systematic, as one would expect from researchers of their caliber. They would observe the selected region of sky, identify candidate galaxies based on their appearance and brightness, and then obtain spectra of these objects to determine their redshifts, which in turn allowed them to calculate approximate distances using the relationship between redshift and recession velocity that follows from the expansion of the universe. This spectroscopic component of the work was essential, because without redshift measurements, one could only see the two-dimensional projection of galaxies onto the sky, like looking at a photograph of a forest and being unable to tell which trees are nearby and which are far in the background. The redshifts provided the crucial third dimension, allowing the astronomers to place each galaxy at its proper distance and thus to map out the true three-dimensional distribution of matter in that particular direction. As the observations accumulated and the team began to compile their measurements into a coherent picture of the galaxy distribution toward Boötes, something unexpected began to emerge from the data, though at first it was not clear whether this unexpected thing was real or merely the result of some subtle error in their procedures. What they were finding, or rather what they were failing to find, was galaxies. In the cone-shaped survey volume they were examining, extending out to distances of several 100 million light-years, there appeared to be a region that was almost completely empty, a vast stretch of space that contained hardly any galaxies at all where standard cosmological expectations would have predicted thousands of them. The numbers themselves were striking in their disparity. Based on the average density of galaxies that had been measured in other directions and at similar distances, the team would have expected to find something in the neighborhood of 2,000 or more galaxies within the volume they were surveying, give or take some reasonable amount of natural variation that one always expects when dealing with cosmic structures that are not perfectly uniform. Instead, what their careful counting revealed was something closer to 60 galaxies scattered through this enormous expanse of space, a number so small in comparison to expectations that it seemed, at first, almost certainly to be wrong. The initial assumption, and this is a perfectly reasonable assumption for any careful scientist to make when confronted with data that dramatically contradicts expectations, was that something must have gone wrong with the observations themselves. Perhaps there was a problem with the equipment, some malfunction or misalignment that was causing them to miss galaxies that were actually present in the survey field. Perhaps there was some form of contamination or interference that was corrupting the data in ways that were not immediately obvious. Perhaps the spectrograph was behaving unexpectedly, or the photographic plates were not recording light as faithfully as they should, or some other technical difficulty was introducing a systematic bias that made the region appear emptier than it truly was. Kirshner and his colleagues spent considerable effort investigating these possibilities, checking and rechecking their equipment, reviewing their procedures, and looking for any plausible explanation that would allow the data to be dismissed as erroneous. This is, after all, what responsible scientists do when their results appear to contradict established understanding. They examine every possible source of error before concluding that they have discovered something genuinely new about the universe. The history of science is filled with apparent discoveries that turned out to be instrumental artifacts or procedural mistakes, and no researcher wants to announce a major finding only to have it collapse under scrutiny because they failed to check whether their equipment was working properly. But as the investigation continued, no such errors could be identified. The equipment appeared to be functioning correctly. The procedures were sound. When they observed other regions of sky using the same methods and the same instruments, they found the expected numbers of galaxies at the expected distances, which indicated that there was nothing systematically wrong with their approach. The emptiness they were detecting in the direction of Boötes appeared to be, as far as they could determine, a genuine feature of the universe itself rather than an illusion created by faulty observation. The void they had discovered, though its boundaries would be refined and its properties better characterized by later observations, appeared to span an almost incomprehensible volume of space. The approximate diameter of this empty region was eventually determined to be somewhere in the neighborhood of 330 million light-years, which is a number that is difficult for the human mind to grasp in any intuitive way, but which can be placed in context by comparing it to other cosmic distances. The observable universe, meaning the spherical region of space from which light has had time to reach us since the beginning of cosmic history, has a diameter of roughly 93 billion light-years. So the Boötes Void, enormous as it is, represents approximately 0.27% of that total diameter, a fraction that sounds small but which corresponds to an actual volume that could contain tens of thousands of galaxies the size of our own Milky Way with room to spare. The formal announcement of this discovery came in October of 1981, when Kirshner, Imler, Schechter, and Schechtman published their findings in the Astrophysical Journal Letters, a venue chosen for its role in rapidly disseminating significant new results to the astronomical community. The paper, like most scientific papers, was written in the measured and precise language of professional research, presenting the observations, describing the methodology, acknowledging the possibilities of error, and drawing only those conclusions that the data could reasonably support. There was no sensationalism in the text, no breathless proclamations about having discovered the largest empty space ever found, just a careful accounting of what had been observed and what it seemed to imply about the structure of the universe on very large scales. The response from the astronomical community was a mixture of interest and healthy skepticism, which is precisely the response that any surprising new claim should receive. Other researchers began to examine the same region of sky, using their own instruments and their own methods, to see whether they could confirm the existence of this apparently vast emptiness or whether some subtle flaw in the original work might eventually come to light. Over the months and years that followed, confirmation did indeed arrive, as independent observations found the same peculiar absence of galaxies in the direction of Boötes, and the void gradually transformed from a curious anomaly into an accepted feature of cosmic cartography. The discovery also prompted theorists to consider what processes might have created such an enormous empty region in a universe that was supposed to have begun in an almost perfectly uniform state. The cosmic microwave background radiation, which provides a snapshot of the universe when it was only a few 100,000 years old, shows that matter was distributed very evenly at that early time, with only the tiniest fluctuations in density from place to place. For a void as large as the one in Boötes to exist today, something must have amplified those tiny initial fluctuations over billions of years, allowing matter to drain away from certain regions and accumulate in others, leaving behind vast expanses of nearly empty space surrounded by the filaments and walls and clusters where galaxies congregate in their hundreds and thousands. Robert Kirshner himself would go on to a distinguished career that included many other contributions to astronomy, including important work on Type Ia supernovae that would eventually help establish that the expansion of the universe is accelerating, a discovery that earned the 2011 Nobel Prize in Physics for some of his collaborators. But the 1981 discovery of the Boötes Void remains a notable early chapter in his scientific story, a reminder that sometimes the most interesting things astronomers find are not the bright objects that announce themselves boldly in telescope images, but the dark and quiet absences where light and matter seem to have chosen, for reasons we are still working to fully understand, simply not to be. The coordinates that Kirshner and his team examined, that patch of sky near right ascension 14 hours and 50 minutes and declination plus 46 degrees, continues to be studied by astronomers today, with more sophisticated instruments and more precise measurements than were available in 1981. The void is still there, still empty, still one of the largest known underdense regions in the observable universe. A quiet monument to the curiosity of four researchers who pointed their telescope at an unremarkable region of sky and found, quite unexpectedly, almost nothing at all. In the years that followed that initial discovery at the Center for Astrophysics, the astronomical community turned its collective attention toward verifying what Kirshner, Imler, Schechter, and Schechtman had reported. Science, as you may know, proceeds not through single discoveries but through careful repetition and expansion, through many eyes looking at the same region of sky with different instruments and from different vantage points. And the Boötes Void required precisely this kind of patient confirmation before it could be accepted as a genuine feature of our universe rather than some peculiar artifact of limited observation. The 1980s brought a series of expanded surveys that reached deeper into the void and examined its surrounding regions with increasing precision. Astronomers at Kitt Peak National Observatory in Arizona, that quiet mountain facility where the night skies remain dark and the air stays remarkably still, devoted considerable telescope time to mapping the galaxies in and around the constellation Boötes. They used the Mile 4-meter telescope, which at that time ranked among the largest optical instruments in the Northern Hemisphere, and they gathered redshift measurements for hundreds of additional galaxies in the general vicinity of the void. These observations, conducted over many observing runs spanning several years, consistently confirmed the essential finding that had so surprised the original team. The emptiness was real, and it was vast, and it showed no signs of being merely a gap in our knowledge rather than a gap in the actual distribution of matter. Simultaneously, astronomers working in the Southern Hemisphere contributed their own observations from Cerro Tololo Inter-American Observatory, perched high in the Chilean Andes where the Pacific air creates some of the most stable atmospheric conditions anywhere on Earth. While the Boötes Void itself lies in the northern sky and cannot be observed directly from Chile, the surveys conducted at Cerro Tololo mapped the large-scale structure in other directions, providing crucial context for understanding whether voids of this magnitude might be common or whether Boötes represented something truly exceptional. These southern surveys revealed other voids, certainly, but none quite so large or so empty as the one that had appeared in the Boötes data, which only added to the scientific interest in understanding how such an enormous empty region could have come to exist. Throughout the 1980s, the picture became progressively clearer as more and more redshift measurements accumulated in the astronomical databases. Each new galaxy whose distance was measured either added to the population within the void, which happened rarely, or confirmed that the void's boundaries held firm, which happened far more often. The techniques for measuring redshifts improved during this period as well, with electronic detectors called charge-coupled devices gradually replacing the photographic plates that had been standard equipment for decades. And these new detectors allowed astronomers to measure the spectra of fainter and more distant galaxies with greater accuracy and in less observing time. The work of Gregory Oldering in the 1990s brought a new dimension to the study of the void by incorporating data from the Infrared Astronomical Satellite, commonly known as IRAS, which had surveyed the entire sky at infrared wavelengths during its operational period in 1983. Infrared light passes through the dust that obscures visible light, and the IRAS survey had detected galaxies that might have been missed by optical surveys due to dust either within those galaxies themselves or along the line of sight from Earth. Oldering carefully cross-referenced the IRAS data with existing optical catalogues and redshift surveys, constructing a more complete census of galaxies in the Boötes region and refining the precise boundaries of the void with greater confidence than had been possible before. This infrared approach proved particularly valuable because it addressed one of the lingering concerns about the void's apparent emptiness. Perhaps, some astronomers had wondered, the void contained numerous galaxies that simply happened to be faint at visible wavelengths or obscured by intervening material, and perhaps a survey at different wavelengths would reveal a hidden population that optical telescopes had failed to detect. The IRA's data, however, showed no such hidden population. The void remained empty even when viewed through the lens of infrared astronomy, and Aldering's work helped to establish that the emptiness was genuine across multiple wavelengths of light. His careful analysis also produced improved measurements of the void's extent and shape, contributing to the emerging consensus that the Boötes Void represented one of the largest known structures, or perhaps one should say one of the largest known absences of structure, in the observable universe. The turn of the millennium brought with it the Sloan Digital Sky Survey, an ambitious project that would eventually map the positions and distances of millions of galaxies across a substantial fraction of the sky. The SDSS, as it came to be known, employed a dedicated telescope at Apache Point Observatory in New Mexico, equipped with specialized instruments designed specifically for the efficient measurement of galaxy redshifts on an unprecedented scale. Beginning in the year 2000 and continuing through multiple phases over the subsequent decades, the Sloan survey systematically observed the northern sky, including the region containing the Boötes Void, and accumulated data of remarkable quality and completeness. The SDSS data allowed astronomers to map the void's boundaries with precision that would have seemed almost magical to the researchers of the 1980s. Where earlier surveys had measured the distances to hundreds or at most a few thousand galaxies in the relevant region, the Sloan survey provided redshifts for tens of thousands of galaxies surrounding the void and confirmed, with statistical certainty, the locations of the sparse few dozen galaxies that actually resided within its interior. The three-dimensional maps produced from SDSS data showed the void as a clearly defined bubble in the cosmic web, surrounded by the filaments and walls of galaxies that characterize the large-scale structure of the universe, and standing out unmistakably as a region where the normal density of matter simply does not apply. According to these detailed surveys, the Boötes Void spans approximately 330 million light-years in diameter, a distance so vast that light itself requires 1/3 of a billion years to cross from one side to the other. Its center lies roughly 700 million light-years from Earth, which places it at a significant but not extreme cosmological distance. At such a distance, we observe the void as it existed some 700 million years ago, since the light reaching our telescopes today departed from those distant regions long before complex life had arisen on our own planet. The void is older now, of course, and may have evolved in subtle ways during the time it has taken for its light to reach us, but such evolution is gradual on cosmic timescales, and the essential character of the void as an underdense region would not have changed dramatically. The shape of the void, as revealed by these comprehensive surveys, is roughly spherical but exhibits the kind of slight irregularities that one would expect from a natural phenomenon rather than from some idealized geometric construction. Its boundaries are not sharp walls but rather transitional regions where the galaxy density gradually increases from the profound emptiness of the interior to the more typical cosmic abundance of the surrounding space. Some portions of the boundary extend outward farther than others, giving the overall shape a somewhat lumpy quality, like a soap bubble that has been gently distorted by uneven air currents. This irregular spherical form is consistent with theoretical expectations for how voids grow and evolve under the influence of gravity, expanding into the surrounding matter and developing slightly asymmetric shapes due to the uneven distribution of mass in their neighborhood. Within this enormous volume, the surveys have identified approximately 60 known galaxies, a number that might sound substantial until one considers the size of the region in question. A typical volume of space equivalent to the Boötes Void would be expected to contain roughly 10,000 galaxies, based on the average cosmic density of matter as measured in other parts of the universe. The void therefore contains only about 0.6% of the normal galactic population, or roughly one galaxy for every 170 that would ordinarily be found in such a volume. The galaxies that do reside within the void tend to cluster together in a loose tube-like structure running through the interior, as if even the sparse population that exists there has sought out the company of its few neighbors rather than spreading evenly throughout the empty space. This extraordinary emptiness has inspired astronomers to contemplate what the universe might look like from a vantage point inside the void, and the results of such contemplation offer a striking illustration of just how isolated such a location would be. If our own Milky Way galaxy were transported to the center of the Boötes Void, the night sky would appear vastly emptier than the one we actually observe. The nearest large galaxies would lie so far away that their detection would require instruments of considerable sophistication, and the general discovery that our universe contains other galaxies beyond our own would have been significantly delayed. This thought experiment suggests that astronomers working from a hypothetical Earth at the center of the Boötes Void would not have discovered the existence of external galaxies until the 1960s. Rather than the 1920s when Edwin Hubble first demonstrated that the spiral nebulae were in fact distant island universes far beyond the boundaries of the Milky Way. Hubble made his discovery using the 100-inch telescope at Mount Wilson Observatory, which allowed him to resolve individual stars in the Andromeda galaxy and thereby prove its extragalactic nature. From the center of the void, Andromeda and all the other nearby galaxies that aided Hubble's work would simply not exist in our cosmic neighborhood, and astronomers would have needed to wait several more decades until telescopes became powerful enough to detect the distant galaxies that would represent our nearest neighbors in that lonely location. This delay of some 40 years might not seem enormous in the grand sweep of cosmic time, but it serves to emphasize just how profoundly empty the Boötes Void truly is. Our understanding of the universe expanded dramatically in the decades between the 1920s and the 1960s, encompassing the discovery of the expanding universe, the development of the Big Bang theory, and the first measurements of cosmic distances on truly vast scales. An astronomical civilization beginning this work 4 decades later would have developed a rather different intellectual history, one shaped by the local emptiness that surrounded them and the relatively recent revelation that they were not alone in the cosmos. The confirmation of the Boötes Void through multiple independent surveys using different telescopes, different wavelengths of light, and different measurement techniques represents a thorough example of the scientific process working as it should. A surprising initial discovery prompted careful follow-up observations, which in turn led to refined measurements and deeper understanding. The void did not shrink away or reveal itself to be an illusion as the data accumulated. Instead, it grew more certain, more precisely defined, and more clearly established as a genuine feature of the cosmic landscape. Today, the existence of the Boötes Void is not a matter of debate among astronomers, but rather an accepted fact that must be accounted for in our theories of how the universe came to possess the structure we observe. The great surveys of the late 20th and early 21st centuries have placed it firmly on the map of the cosmos, a region where the ordinary rules of galactic abundance simply do not apply, where emptiness reigns on a scale that challenges even our well-developed capacity for imagining vast distances and sparse populations. The void remains there, some 700 million light-years away, patiently demonstrating that the universe contains not only the magnificent concentrations of matter that we call galaxies and galaxy clusters, but also these remarkable expanses of almost nothing at all. When we look out into the universe and try to understand its structure, we must first appreciate what our best theories tell us we ought to see, because only then can we recognize when something does not quite fit, when the cosmos has arranged itself in ways that give our models pause. And the Boötes Void, as we shall gently explore, is one such arrangement that asks us to look more carefully at our assumptions about how empty spaces come to be. The story of voids, like so many stories in cosmology, begins with the Big Bang itself, that incomprehensibly hot and dense state from which all of space and time emerged approximately 13.8 billion years ago. And in those earliest moments, the universe was remarkably smooth, almost perfectly uniform in its distribution of energy and matter, but not quite, not entirely, because there were tiny fluctuations, minuscule variations in density that would prove to be the seeds of everything we see today. Every galaxy, every cluster, every vast cosmic web, and every empty void between them. These primordial fluctuations were almost unimaginably small, variations of perhaps 1 part in 100,000 from the average density, which means that if you could have measured the density of the early universe in different places, you would have found that most regions were nearly identical, with only the slightest differences, the gentlest whispers of variation. Yet these whispers were enough, because gravity is patient, and gravity is persistent, and over billions of years, gravity took these tiny seeds and grew them into the structures we observe today. We can actually see these ancient fluctuations preserved in the cosmic microwave background radiation, that faint afterglow of the Big Bang that permeates all of space, first detected accidentally in 1964 and mapped with increasing precision by satellites such as COBE, WMAP, and most recently the Planck Observatory. And when cosmologists study these maps, they see a snapshot of the universe as it was roughly 380,000 years after the Big Bang, a time when the cosmos had cooled enough for atoms to form and light to travel freely. And in that snapshot, the tiny temperature variations correspond directly to those primordial density fluctuations, the blueprint from which all cosmic structure would eventually emerge. The physics of what happened next is both elegant and gradual, and it unfolds according to principles that we understand reasonably well, though always with room for surprise. And the essential mechanism is this: that regions which started with slightly higher density than average had slightly stronger gravitational pull, which meant they attracted matter from their surroundings, growing denser still, while regions that started with slightly lower density found their matter being pulled away, becoming emptier over time. And this process, sometimes called gravitational instability, operated continuously across billions of years, amplifying those initial whispers of variation into the dramatic contrasts we observe in the modern universe. The result of this long gravitational evolution is what cosmologists call the cosmic web, a vast interconnected structure of filaments and walls and nodes, with galaxies concentrated along these features and enormous voids occupying the spaces between them. And if you could somehow step back and view a large enough volume of space, perhaps 1 billion light-years on a side, you would see this web-like pattern quite clearly, with dense clusters of galaxies sitting at the intersections of filaments, the filaments themselves stretching between clusters like gossamer threads, and the voids appearing as great bubbles of relative emptiness, regions where galaxies are sparse or absent altogether, carved out by the same gravitational processes that built up the denser structures around them. To understand what voids should look like in quantitative detail, cosmologists have turned to computer simulations. Because the mathematics of gravitational evolution involving billions of particles is far too complex to solve with pencil and paper, and among the most influential of these simulations is the Millennium Simulation, conducted by the Virgo Consortium and published in 2005, which traced the gravitational evolution of more than 10 billion particles representing dark matter in a cubic volume of space roughly 2 billion light-years on a side, following their motions from shortly after the Big Bang to the present day. And when the simulation was complete, it produced a universe that looked remarkably like the one we observe, with the same web-like structure, the same statistical distribution of clusters and filaments and voids, which gave cosmologists confidence that their understanding of cosmic structure formation was fundamentally correct. The Millennium Simulation and others like it allow researchers to measure what might be called void statistics, the expected sizes, shapes, and distributions of cosmic voids under the standard model of cosmology, known as lambda CDM, where lambda refers to dark energy and CDM stands for cold dark matter. And what these simulations consistently show is that voids come in a range of sizes, with smaller voids being more common and larger voids being progressively rarer, following statistical distributions that can be calculated and compared with observations. And the typical void that emerges from these simulations spans somewhere between 30 and 150 million light-years in diameter, with most falling toward the smaller end of this range, and voids significantly larger than 150 million light-years become increasingly improbable, not impossible, but expected to be rare. One researcher who has devoted much of his career to understanding void formation and dynamics is Rien van der Weygaert at the University of Groningen in the Netherlands, who has developed detailed theoretical frameworks for how voids evolve over cosmic time, and his work has illuminated several important aspects of void behavior, including the way that voids are not static features but dynamic ones, continuously growing and changing as the universe expands and matter redistributes itself under gravity. And van der Weygaert has described how voids tend to expand as their matter is pulled toward the denser regions surrounding them, stretching and growing over billions of years, though this expansion happens at a gentle pace that matches the gradual rhythm of cosmic evolution. Among the concepts that van der Weygaert and his colleagues have explored is what might be called the void hierarchy, the idea that the void population is not fixed but evolves through a process of merging and absorption, where smaller voids that form early in cosmic history can gradually combine into larger voids as the thin walls separating them are pulled apart or absorbed into surrounding structures. And this hierarchical growth means that the largest voids we observe today may not have formed as single large underdensities, but rather as collections of smaller voids that merged over billions of years, building up larger and larger empty regions through a gradual process of coalescence, rather like how small soap bubbles can merge into larger ones when the films between them break down. This void hierarchy provides one possible mechanism for producing exceptionally large voids, because if several smaller voids happen to form in adjacent regions and subsequently merge, the resulting structure could be larger than any single void that formed independently, and this merging process is influenced by the local environment, the arrangement of filaments and walls and clusters that surround the void, meaning that the sizes of the largest voids depend somewhat on the particular history of their surroundings, introducing an element of cosmic chance into the statistics of void sizes. Though even accounting for this merging process, The standard models place limits on how large a void can plausibly grow within the age of the universe. When we consider the statistics of voids across the universe as a whole, we find a striking asymmetry between volume and matter. Because voids occupy roughly 80% of the total volume of the universe, vast regions of relative emptiness stretching in all directions. Yet these enormous volumes contain only about 20% of all the matter, with the remaining 80% of matter concentrated into the filaments and walls and clusters that make up only 20% of the volume. And this profound asymmetry reflects the cumulative effect of billions of years of gravitational evolution, as matter has been steadily drained from the void regions and accumulated in the denser structures, leaving behind these great empty bubbles that dominate the volume of space while hosting relatively little of its contents. The density inside a typical void is perhaps 10 to 20% of the average cosmic density, meaning that while voids are often described as empty, they are not truly devoid of matter, merely depleted, and the galaxies that do exist within voids tend to be different from those in denser environments, often smaller, blue, and more actively forming stars, as if the quieter environment of the void allows them to evolve at their own unhurried pace, undisturbed by the interactions and mergers that shape galaxies in crowded regions. And studying these void galaxies provides cosmologists with a kind of control sample, a way to understand how galaxies develop when left largely to themselves. Now we come to the question that makes the Boötes Void so interesting from a theoretical perspective. Because when we compare its size to the expectations from our standard cosmological models, we find that it sits uncomfortably at the edge of what those models predict, and perhaps beyond. For the Boötes Void spans approximately 250 to 330 million light-years in diameter, depending on how precisely we define its boundaries. And this makes it roughly 2 to 3 times larger than the largest voids that typically appear in simulations like the Millennium simulation, placing it in the far tail of the expected size distribution, a statistical outlier that requires some explanation. The lambda CDM model, which has been remarkably successful at explaining most features of cosmic structure, makes specific predictions about the distribution of void sizes. And while it allows for some very large voids to exist as rare statistical fluctuations, the Boötes Void challenges these predictions by being larger than most simulations readily produce. And this does not necessarily mean that our cosmological model is wrong, for any sufficiently large universe will contain some structures that are statistically unlikely, merely by chance. But it does prompt cosmologists to examine their assumptions carefully and to consider whether the Boötes Void might be telling us something we have not yet fully understood. One way to frame this challenge is to ask what the probability is of finding a void as large as the Boötes Void in a universe governed by lambda CDM cosmology. And various researchers have attempted such calculations with somewhat different results depending on their methods and assumptions. But the general finding is that while such a void is not strictly impossible, it is sufficiently improbable that its existence warrants careful attention, particularly if other similarly large voids were to be discovered, because a single unlikely event can be attributed to chance. But a pattern of unlikely events suggests that our models may be missing something. Several possible explanations have been proposed for how a void this large might arise within the standard cosmological framework, including the void hierarchy mechanism we discussed earlier, where multiple smaller voids merged over billions of years to produce a single exceptionally large structure. And this possibility is supported by the observation that the Boötes Void is not perfectly empty but contains some galaxies and possibly some internal structure that might represent the remnants of the walls that once separated smaller voids before they merged. though determining whether this explanation is sufficient requires detailed comparison between observations and simulations, work that continues today. Another possibility is that the Boötes Void corresponds to an unusually large primordial underdensity, a region where the initial density fluctuations happen to be particularly deep and extended, setting the stage for exceptional void growth over the subsequent billions of years. And while such fluctuations are rare in the statistical distribution predicted by standard cosmology, they are not forbidden, and the observable universe is large enough that we might expect to find a few such regions if we survey a sufficient volume, though quantifying exactly how rare is a matter of ongoing research and depends on details of the primordial fluctuation spectrum that we are still working to constrain. As you rest here, listening to these gentle explanations of cosmic structure, it may be soothing to consider that even the emptiest places in the universe have their origins in those ancient density fluctuations, those tiny whispers of variation that gravity so patiently amplified over 13.8 billion years. And whether the Boötes Void represents an extreme but acceptable outcome of standard physics or hints at something our models have not yet captured, it remains a fascinating feature of the cosmos. A great quiet space carved out by the same forces that built the galaxies and clusters that surround it, and understanding how it came to be is part of our ongoing effort to comprehend the universe in all its vast and varied structure. When astronomers first mapped the Boötes Void and confirmed its extraordinary emptiness, they naturally wondered whether anything at all existed within that vast expanse, and the answer, as it turns out, is yes, though the galaxies that do inhabit this region are so few and so widely separated that their presence only emphasizes the profound isolation of the space they occupy. Current surveys suggest that somewhere between 60 and perhaps 100 galaxies have been identified within the void boundaries, which sounds like a reasonable number until you remember that a comparable volume of average universe would contain several thousand galaxies. And so these scattered inhabitants represent a population deficit of roughly 90% or more, making each one a rather lonely island in an ocean of emptiness that stretches for hundreds of millions of light-years in every direction. The early efforts to understand what, if anything, lived inside the Boötes Void received a significant contribution in 1987, when J. Moody and colleagues published their findings about the spatial distribution of the few galaxies that could be found within this enormous cavity. Rather than being scattered randomly throughout the void like dust motes drifting in a darkened room, these galaxies appeared to be arranged in a loose structure, something that the researchers described as a tube or filament threading through the otherwise empty volume. This tubular arrangement suggested that even within the void, the same gravitational processes that organize matter elsewhere in the universe were at work, though operating on far more meager raw materials, and the galaxies had collected along what might be thought of as a very tenuous cosmic string, a faint echo of the great filaments and walls that contain most of the universe's visible matter. This 1987 study was important because it demonstrated that the void was not simply a uniform emptiness but contained subtle structure of its own, and it raised interesting questions about how such a filament might have formed and persisted in a region so lacking in the gravitational influence of surrounding matter. The tube of galaxies that Moody and colleagues identified runs roughly through the central regions of the void, and while it is a pale shadow of the great galaxy chains found in denser cosmic neighborhoods, it represents one of the few organizing principles that astronomers have been able to identify in this otherwise featureless volume, a gentle reminder that gravity continues its patient work even in the most underpopulated reaches of space. Among the specific galaxies that have been catalogued within the Boötes Void boundaries, Several have received individual attention from researchers attempting to understand how these isolated systems differ from their counterparts in more crowded environments. Objects catalogued in various survey databases carry designations that reflect the systematic naming conventions of modern astronomy. And while these alphanumeric identifiers lack the poetry of names like Andromeda or the Whirlpool Galaxy, they represent real stellar systems containing billions of stars, each one a genuine galaxy that happens to exist in extraordinary solitude. Some of these void inhabitants have been observed with sufficient detail to determine their morphological types, their colors, their rates of star formation, and other properties that allow astronomers to compare them meaningfully with galaxies found in denser cosmic neighborhoods. What emerges from these observations is a picture of galaxies that are, in many cases, quite different from their counterparts elsewhere, and these differences appear to stem directly from their isolated circumstances. The galaxies within the Boötes Void tend to be blue in color, which in astronomical terms indicates that they contain populations of hot, young stars and are actively engaged in the process of forming new stellar generations. This blueness stands in contrast to the redder colors often found in galaxies that inhabit dense clusters, where interactions with neighbors and the hot gas of the cluster environment tend to strip away the raw materials needed for star formation, leaving behind older, cooler stellar populations that glow with the ruddy light of aged suns. The concept of void galaxies has become a recognized category in extragalactic astronomy, referring to those stellar systems that exist in the underdense regions of the cosmic web rather than along the filaments and walls and nodes where most galaxies congregate. These void inhabitants have attracted particular attention from researchers interested in understanding how environment shapes galactic evolution, because they represent a kind of control group, galaxies that have developed largely in isolation and can therefore reveal what properties are intrinsic to galaxies themselves and what properties result from interactions with neighbors and the surrounding cosmic environment. Michael Vogeli at Drexel University has been among the researchers who have devoted significant attention to the study of void galaxies and how they differ from their counterparts in denser regions. His work, along with that of his collaborators, has helped establish that void galaxies do indeed evolve differently from galaxies in crowded environments, and that this difference manifests in measurable ways, including their colors, their morphologies, their star formation rates, and their gas content. The void environment, characterized by its lack of neighboring galaxies and its lower overall matter density, creates conditions under which galaxies can develop without the disturbances and interactions that are routine elsewhere in the universe. One of the most significant differences is simply the absence of galaxy interactions and mergers, those gravitational encounters that are so common in denser cosmic neighborhoods and that play such an important role in shaping galactic evolution. When galaxies pass close to one another, their mutual gravitational attraction can distort their shapes, trigger bursts of star formation, strip away gas and dust, and in some cases lead to complete mergers where two galaxies combine into a single larger system. These interactions are thought to be responsible for much of the diversity we see in galaxy morphologies, and they represent one of the primary mechanisms by which galaxies grow and evolve over cosmic time. Within the Boötes Void, such interactions simply do not happen with any significant frequency, because the galaxies are so widely separated that they almost never pass close enough to influence one another gravitationally. A galaxy in the void might go its entire existence without experiencing a close encounter with another stellar system, and this isolation allows it to evolve in a fundamentally different manner than galaxies in denser environments. Without the disturbances of passing neighbors, void galaxies tend to retain more regular, undisturbed morphologies, and their star formation can proceed at a more steady, unhurried pace rather than being triggered into bursts by gravitational interactions. The Hubble Space Telescope has contributed observations to the study of void galaxy morphologies, providing the high-resolution imaging needed to examine the structural details of these isolated systems. When astronomers examine void galaxies with sufficient resolution to see their spiral arms, their central bulges, their disk structures and other morphological features, they find systems that often appear remarkably undisturbed, lacking the tidal tails and asymmetries and other signatures of gravitational interaction that are common among galaxies in denser environments. This undisturbed appearance is entirely consistent with their isolated circumstances, confirming that these galaxies have indeed evolved without the gravitational influences that shape their counterparts elsewhere. In 2014, Krekel and colleagues published an important study examining the properties of void galaxies in detail, contributing significantly to our understanding of how these isolated systems compare to galaxies in average cosmic environments. Their work examined various properties of void galaxy populations, including their gas content, their star formation rates, their structural characteristics, and other measurable attributes that allow meaningful comparisons to be drawn. What emerged from this study, and from similar work by other researchers, is a picture of void galaxies as systems that are often gas-rich and actively forming stars. Characteristics that might seem surprising given their isolation, but that actually make sense when one considers that these galaxies have not been subjected to the processes that remove gas from systems in denser environments. The gas richness of void galaxies is particularly interesting because it suggests that these systems have retained more of their original raw materials for star formation than galaxies in clusters and groups, where various processes work to strip gas away. In dense environments, galaxies can lose their gas through ram pressure stripping as they move through hot intracluster medium, through tidal stripping during close encounters with neighbors, and through consumption during the starbursts triggered by interactions. Void galaxies, experiencing none of these processes, tend to hold onto their gas and can therefore continue forming stars at a steady pace over extended periods. The question of nature versus nurture in galactic evolution is one that void galaxies are particularly well suited to address, because they represent systems that have developed largely free from environmental influences. When astronomers ask whether galaxies are shaped primarily by their intrinsic properties, things like their initial mass and angular momentum and gas content, or by their interactions with the cosmic environment around them, void galaxies offer a kind of natural experiment in which the environmental variable has been largely removed. By comparing void galaxies to their counterparts in denser regions, researchers can begin to disentangle the relative contributions of intrinsic properties and environmental effects to galactic evolution. What the evidence suggests is that environment does indeed play a significant role in shaping how galaxies develop, because void galaxies show systematic differences from galaxies in denser regions that cannot be explained by intrinsic properties alone. The bluer colors, the higher gas fractions, the more regular morphologies, the lower rates of interaction and merger, all of these characteristics point to the importance of cosmic environment in determining how a galaxy will evolve over billions of years. At the same time, void galaxies are not radically different from other galaxies in their fundamental properties. They follow the same basic scaling relations between mass, luminosity, and other properties, suggesting that the intrinsic processes of galaxy formation and evolution are broadly similar regardless of environment. The galaxies of the Boötes Void thus serve as a kind of cosmic laboratory, a place where astronomers can study galactic evolution under conditions of unusual isolation and thereby gain insights into the relative importance of internal and external factors in shaping these magnificent stellar systems. Each lonely galaxy in the void, separated from its nearest neighbor by tens of millions of light-years, has followed its own evolutionary path largely undisturbed by outside influences. And by studying these isolated systems, researchers can better understand what features of galaxies are fundamental to their nature and what features result from the complex gravitational dance of cosmic neighborhoods. The few dozen galaxies scattered through the Boötes Void represent a tiny population compared to what might be expected in a comparable volume of average universe, and their sparse distribution only emphasizes the profound emptiness of the region they inhabit. Yet each one is a complete stellar system containing billions of stars, worlds beyond counting, and all the potential for complexity and wonder that any galaxy possesses. Their isolation has shaped their evolution in measurable ways, making them gassier, less disturbed than galaxies that have spent their cosmic lives in crowded neighborhoods. And in studying these differences, astronomers learn something fundamental about how the largest structures in the universe influence the development of the stellar systems within them. A gentle lesson written in the light of lonely galaxies drifting through the emptiest place in the known universe. When we turn to the question of how the Boötes Void came to exist in its present form, we find ourselves in that comfortable territory of scientific uncertainty where multiple explanations coexist, each with its own merits and its own difficulties, and where the honest answer remains, for now, that we simply do not know with certainty which account is correct. This is not a failure of science but rather its natural state when confronting phenomena at the very edges of our observational capabilities. And there is something rather peaceful in acknowledging that the universe still holds questions we have not yet resolved. Let us consider, then, the principal theories that astronomers and cosmologists have proposed over the decades since this remarkable emptiness was first charted, taking each in turn with the unhurried attention it deserves. The first explanation, and perhaps the most conservative in its assumptions, is that the Boötes Void represents nothing more than a statistical fluctuation, an extreme but not impossible outcome of the normal processes that have shaped the distribution of matter throughout the cosmos. In any sufficiently large sample of anything at all, whether we are speaking of rainfall measurements across a continent or the heights of trees in an enormous forest, we expect to find occasional values that sit far from the average, simply by the ordinary workings of probability. The universe, in this view, is rather like a vast and textured fabric, with regions of higher and lower density woven throughout. And if we examine enough of this fabric, we should not be surprised to find a patch here or there where the threads are unusually sparse. This perspective was examined carefully in a 1999 analysis by Elizondo and colleagues, who applied statistical methods to assess whether the Boötes Void falls within the expected range of cosmic variance, that natural scatter we anticipate when matter clumps and clusters under the influence of gravity across billions of years. Their work suggested that while the void is certainly unusual, it is not necessarily so unusual as to require exotic explanations, sitting perhaps at the far tail of a distribution but not entirely beyond it. The difficulty with this interpretation, gentle though it is, lies in the sheer scale of the emptiness we observe. When we calculate the probability of finding a region this large and this underdense arising from ordinary fluctuations, the numbers become rather small, though not vanishingly so, and different researchers using different assumptions about the underlying statistics have reached different conclusions about just how improbable this void truly is. Some find it acceptable within standard models, while others suggest it strains credulity. And so the debate continues in that quiet way that characterizes much of scientific discourse. A second theory proposes that the Boötes Void did not form as a single primordial structure, but rather grew to its present dimensions through the gradual merger of multiple smaller voids over the long course of cosmic time. This explanation draws upon our understanding of how structure evolves in an expanding universe, where gravity pulls matter together into filaments and walls while leaving behind increasingly empty regions in between. Computer simulations of cosmic evolution, including detailed work conducted by Gottlober and colleagues at the Leibniz Institute for Astrophysics in Potsdam, have demonstrated that voids do indeed grow and merge as the universe ages. Smaller underdensities, having formed in the early epochs following the Big Bang, expand and eventually encounter one another, their boundaries dissolving as they combine into progressively larger empty volumes. In this picture, the Boötes Void is not a single ancient feature but rather a composite structure, the end product of many generations of void merger spanning billions of years. The simulations show that such large voids can indeed form through this hierarchical process, given sufficient time and the right initial conditions. And this lends a certain plausibility to the explanation. The challenge for this theory lies in reproducing not just the size of the Boötes Void but its particular characteristics, including its relatively spherical shape and the sharpness of some of its boundaries. Merged voids in simulations often display more irregular geometries, with substructure and asymmetries that reflect their complex formation histories. And while the Boötes Void does show some internal features, its overall coherence presents something of a puzzle. Additionally, the number of extremely large voids we observe in the cosmos may exceed what standard merger scenarios readily produce, though this depends sensitively on the details of the simulations and the assumptions built into them. The third explanation reaches further back in time, proposing that the Boötes Void traces its origins to an extreme underdensity present in the very early universe, imprinted somehow in the primordial conditions that emerged from the epoch of inflation or even earlier. In this view, the void is not merely a statistical fluctuation in the ordinary sense, but represents a genuinely anomalous region where the initial density was markedly lower than its surroundings from the very beginning. Such a primordial underdensity would have expanded more rapidly than the average cosmos, emptying itself of matter as the universe evolved, and would have grown to enormous proportions by the present day precisely because it began with such a pronounced deficit. This interpretation invites comparison with another curious feature of our observed universe, the so-called cold spot in the cosmic microwave background radiation, that ancient light that reaches us from the epoch when the universe first became transparent to photons, some 380,000 years after the Big Bang. The cold spot, detected first by the Wilkinson Microwave Anisotropy Probe, or WMAP, and later confirmed with greater precision by the Planck satellite, appears as a region of the sky where the microwave background is slightly cooler than its surroundings, suggesting either a primordial underdensity or a large void along the line of sight that has imprinted itself on the ancient light through a phenomenon known as the integrated Sachs-Wolf effect. Some researchers have wondered whether similar physics might explain both the cold spot and the Boötes Void, though the two features are not aligned on the sky and their relationship, if any, remains unclear. The Planck data, in particular, provided exquisitely detailed maps of the microwave background, allowing cosmologists to search for subtle correlations between these temperature variations and the large-scale structures we observe in the more recent universe. And while suggestive hints have emerged, no definitive connection has been established. The difficulty with primordial explanations in general lies in their invocation of special initial conditions, which raises the question of how such conditions arose in the first place, and whether they require new physics beyond our standard inflationary model. The fourth theory ventures into more speculative territory, exploring whether exotic physical processes might account for the unusual properties of the Boötes Void. Among the possibilities considered is the idea that dark energy, that mysterious component driving the accelerating expansion of the universe, might not be perfectly uniform throughout space but could vary in concentration from region to region, with consequences for how matter clusters and how voids evolve. If dark energy were somehow more concentrated within the Boötes Void, or if its effects manifested differently there, the local expansion rate might exceed the cosmic average, sweeping matter outward and deepening the emptiness over time. This line of thinking was explored by Tomita in work published around the year 2000, examining how a local void with different expansion properties might affect our observations of the universe more broadly, including our measurements of cosmic acceleration itself. Tomita's analysis considered whether living within or near a large void might create the illusion of accelerated expansion, though subsequent observations have largely ruled out this particular suggestion as an explanation for dark energy. Nevertheless, the broader question of whether voids might exhibit locally different physics remains open, and some researchers continue to investigate whether subtle variations in fundamental parameters might distinguish the interior of the Boötes Void from the cosmos at large. The challenges facing exotic explanations are considerable, including the need for new physics not yet detected in any other context and the difficulty of making testable predictions that distinguish these theories from more conventional accounts. Science rightly holds exotic proposals to a high standard of evidence, and while they are not dismissed outright, they remain minority positions in the ongoing discussion. Each of these theories has found supporters among the community of astronomers and cosmologists who study large-scale structure, and each faces its own particular difficulties that prevent it from achieving consensus acceptance. The statistical fluctuation hypothesis is conservative and requires no new physics, but it struggles to account for the sheer improbability of finding an emptiness quite so large and quite so empty within the volume of universe we have surveyed. The void merger theory aligns well with our understanding of cosmic evolution and receives support from sophisticated simulations, but it does not always reproduce the observed characteristics of the Boötes Void with complete fidelity. The primordial anomaly explanation offers a satisfying narrative of ancient origins, but requires us to accept that the early universe contained exceptionally unusual regions whose cause remains unexplained. And the exotic physics theories, while intriguing, invoke mechanisms for which we have little independent evidence and which may prove unnecessary if more conventional explanations ultimately suffice. This state of affairs, where multiple plausible theories coexist without clear resolution, is not uncommon in cosmology, particularly when we confront phenomena at the largest scales and most extreme conditions. What we can say with confidence is that the Boötes Void exists, that it is remarkably large and remarkably empty by any reasonable standard, and that its presence tells us something important about the processes that have shaped our universe, even if we cannot yet agree on precisely what that something is. The gentle mystery of its origins invites continued observation and continued theoretical work, and future surveys mapping ever larger volumes of the cosmos may eventually reveal whether voids of this size are truly exceptional or merely the largest members of a continuous population. For now, the Boötes Void remains a fascinating puzzle, one whose solution lies somewhere among the theories we have discussed or perhaps in some explanation not yet conceived, waiting to be discovered by generations of astronomers yet to come. And so we come to perhaps the most curious part of our journey, the part where we consider what all this emptiness might actually teach us, what lessons the universe has hidden in its most vacant places, waiting patiently for us to develop the instruments and the mathematics and the simple quiet attention necessary to find them. You see, for a very long time in the history of astronomy, emptiness was simply that, an absence, a place where nothing interesting was happening, a region to be passed over quickly on the way to something more worthy of study. Astronomers pointed their telescopes at bright things, at stars and nebulae and galaxies, because those were the objects that produced light, that announced their presence across the vast distances of space, that seemed to be doing something worth recording. The dark spaces between them were treated rather like the margins of a page, technically present but not really the point of the document. But as our understanding has deepened, as our theories have grown more sophisticated and our instruments more sensitive, we have come to realize that those margins contain information just as important as the text itself, perhaps even more important, because the emptiness tells us things that the filled spaces cannot. One of the most significant things that cosmic voids teach us concerns the nature of dark energy, that mysterious influence that appears to be accelerating the expansion of the universe, pushing galaxies apart from one another at an ever-increasing rate. Dark energy is one of the great unsolved puzzles of modern physics, a phenomenon we can detect through its effects but cannot yet explain in any satisfying fundamental way. We know it comprises roughly 68% of the total energy content of the universe, which makes it by far the dominant component, and yet we do not know what it actually is, whether it is a property of space itself, a new type of field pervading all of existence, or something else entirely that we have not yet imagined. And this is where voids become useful, because they act as natural laboratories for testing our theories about dark energy, places where its effects might be isolated and measured without the complications introduced by dense matter. The work of researchers such as Guilhem Lavaux and Benjamin Wandelt has been particularly illuminating in this regard. Their contributions to void cosmology have helped establish voids as serious tools for precision measurements of the universe, not merely as curiosities but as genuine probes of fundamental physics. The reasoning is elegant in its simplicity. In the dense regions of the universe, where galaxies cluster together and dark matter collects in massive halos, the gravitational effects are strong and complex, with many different influences overlapping and interacting in ways that can be difficult to disentangle. But in the voids, where matter is scarce and gravity is correspondingly weak, the effects of dark energy become proportionally more significant, easier to isolate and measure. By studying how voids grow and evolve over cosmic time, by tracking their sizes and shapes across different epochs of the universe's history, we can place constraints on the nature of dark energy, testing whether it behaves as a simple cosmological constant or whether it varies in some way that might point toward new physics. The emptiness, in other words, is not a place where physics is absent, but rather a place where certain aspects of physics become clearer, like a stage cleared of props so that a single actor can be better observed. There is another phenomenon that makes voids particularly valuable to cosmologists, a subtle effect with a rather grand name, the integrated Sachs-Wolf effect. To understand this, we must think about the cosmic microwave background, that faint glow of ancient light that fills all of space, the remnant radiation from the hot early universe that has been traveling toward us for nearly 14 billion years. This light began its journey when the universe was only about 380,000 years old, long before any stars or galaxies had formed, and it has been streaming through the cosmos ever since, gradually cooling and stretching as space itself expanded. When we observe this light today, it appears as a nearly uniform glow coming from all directions, with a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. But it is not perfectly uniform. There are tiny fluctuations, variations of just a few parts in 100,000, and these fluctuations carry encoded within them a wealth of information about the universe's history and composition. The integrated Sachs-Wolf effect adds to these fluctuations in a particular way. When a photon of the cosmic microwave background passes through a void, it enters a region where the gravitational potential is slightly different from the average, a shallow well rather than a deep one. As the photon falls into this well, it gains a tiny amount of energy, and as it climbs out the other side, it loses energy again. In a static universe, these effects would exactly cancel, and the photon would emerge with the same energy it started with. But our universe is not static. It is expanding, and that expansion is accelerating under the influence of dark energy. This means that during the time the photon spends crossing the void itself is stretching, becoming a bit shallower, so that the photon has to climb out of a shallower well than the one it fell into. The result is that the photon loses a net amount of energy during its passage, emerging very slightly redder, very slightly cooler than it was before. When we observe the cosmic microwave background in the direction of a large void, we therefore expect to see a slight cold spot, a region where the ancient light is just a tiny bit cooler than the surrounding sky. This effect is extremely subtle, far too small to notice in any individual measurement, but when we combine observations of many voids and compare them statistically to our theoretical predictions, the signal emerges from the noise, a gentle confirmation that our understanding of gravity and dark energy and the structure of the universe is at least approximately correct. The emptiness speaks to us through this ancient light, adding its quiet voice to the chorus of evidence that supports our modern cosmological models. Of course, our current observations are limited by the technology available to us, by the sensitivity of our detectors and the area of sky we have been able to survey in sufficient detail. But new instruments are coming online that will transform our ability to study cosmic voids and extract the information they contain. The Euclid Space Telescope, a mission of the European Space Agency, launched in July of 2023 from Cape Canaveral aboard a SpaceX Falcon 9 rocket. It is now stationed at the second Lagrange point, about 1.5 million kilometers from Earth, where it is conducting a survey of the extragalactic sky that will eventually cover roughly 15,000 square degrees, more than a third of the entire celestial sphere. Euclid carries both a visible light camera and a near-infrared spectrometer, and over the course of its mission it will measure the positions and shapes of billions of galaxies, tracing the large-scale structure of the universe out to distances of 10 billion light-years. This unprecedented census will allow astronomers to identify and characterize voids with a precision never before possible, mapping their boundaries, measuring their sizes and shapes, and tracking how these properties have changed over cosmic time. Complementing Euclid's work from space will be the Vera C. Rubin Observatory, a ground-based facility in northern Chile that is preparing to conduct the Legacy Survey of Space and Time, often abbreviated as LSST. When this survey begins, the Rubin Observatory will photograph the entire visible southern sky every few nights using the largest digital camera ever built for astronomy, a 3.2 billion pixel instrument capable of detecting extremely faint and distant galaxies. Over the course of a decade, it will observe roughly 20 billion galaxies, creating a three-dimensional map of the universe that will be both deeper and more complete than anything we have achieved before. The combination of these two surveys, one from space and one from the ground, one in the northern sky and one in the south, will give us our first truly comprehensive view of the cosmic web and the voids that permeate it, allowing us to test our theories of dark energy with far greater rigor than is currently possible. The statistical characterization of voids has a distinguished history that stretches back several decades, and among the pioneers of this work we must mention Jan Einasto, an Estonian astronomer based at Tartu Observatory who has spent much of his career studying the large-scale structure of the universe. Einasto's contributions to our understanding of the distribution of galaxies and the properties of supervoids have been substantial and lasting, helping to establish the mathematical frameworks we use to describe these enormous empty regions. His work on supervoid statistics, on the typical sizes and frequencies of the largest voids, has informed our expectations and guided subsequent observations. When we speak of voids today, when we discuss their role in cosmology and their implications for fundamental physics, we are building on foundations laid in part by researchers like Einasto, who saw the importance of emptiness when many others were still focused exclusively on the bright concentrations of matter. There is also a philosophical dimension to consider, one that is perhaps best contemplated in a quiet moment, when the mind is relaxed and receptive to speculation. Imagine, if you will, an intelligent species arising not here on Earth, in our relatively crowded corner of the cosmos, but somewhere deep within the Boötes Void or one of its siblings, on a planet orbiting a solitary star in a galaxy that drifts alone through that vast emptiness. What would such beings conclude about the nature of the universe? From their vantage point, the night sky would be almost entirely dark, with no Milky Way stretching overhead, no neighboring galaxies visible to the naked eye, only the distant cold glow of the cosmic microwave background and perhaps a handful of the very brightest objects on the far edge of detectability. They might develop astronomy eventually, might build telescopes capable of spotting the faint smudges of galaxies hundreds of millions of light-years away, but their intuitive sense of the cosmos would be profoundly different from ours. They would grow up under empty skies, would take emptiness as the default condition of existence, and would find the notion of crowded galactic clusters as strange and exotic as we find their solitude. The universe would be the same in both cases, the same physical laws operating on the same matter and energy, but the lived experience of cosmology, the felt sense of what it means to exist in space, would be utterly transformed. This thought experiment touches on something called the Copernican principle, named after Nicolaus Copernicus, who famously displaced the Earth from the center of the universe by demonstrating that it orbits the Sun rather than the other way around. The Copernican principle is a kind of philosophical guideline, a caution against assuming that our position in the universe is in any way special or privileged. When we look out at the cosmos, we should not assume that what we see from here is typical of what would be seen from everywhere, nor should we assume that our particular location was somehow chosen or destined or meaningful. We are simply here, in this galaxy, in this cluster, in this filament of the cosmic web, and there is nothing about our address that makes it more important or central than any other. But the interesting corollary of this principle, the part that the existence of voids forces us to confront, is that our position is also not typical. We do not live in a void. We do not live in the densest part of a supercluster. We occupy a location that is in some sense middling, neither exceptionally crowded nor exceptionally empty. This is neither special nor average, simply one possibility among many, and our picture of the universe has been shaped by this particular vantage point in ways we are only beginning to appreciate. Perhaps the most profound lesson that emptiness teaches us is about the nature of the dark matter that we cannot directly see. Dark matter makes up roughly 27% of the universe, far outweighing all the ordinary matter that composes stars and planets and people. And yet we have never detected a dark matter particle directly, have never captured one in a laboratory or observed one producing light. We know it exists only through its gravitational effects, through the way it bends light, through the way galaxies rotate, through the way large-scale structures form. And here voids play a crucial role, because they allow us to trace the dark matter scaffolding by observing what is not there. The galaxies we see are not distributed randomly. They follow the underlying dark matter, clustering where it clusters, avoiding where it is absent. By mapping the voids, by measuring their sizes and shapes and positions, we are in effect mapping the dark matter that defines their boundaries. We trace what we cannot see by cataloguing the absences, by paying careful attention to the places where ordinary matter has chosen not to gather. The emptiness becomes a kind of negative image, a shadow that reveals the shape of something invisible. This is one of the beautiful paradoxes of modern cosmology, that we learn about the universe not only by studying what is present but by studying what is missing, that absence is as informative as presence, that the darkness tells us things the light cannot. The voids are laboratories and textbooks and philosophical provocations, all at once, and as we develop better instruments and more sophisticated theories, they will continue to teach us, continue to surprise us, continue to remind us that the universe is stranger and more subtle than our everyday experience would suggest. But these revelations come slowly, patiently, as science always does, accumulating evidence and refining understanding in a process that spans generations. There is no rush. The voids have been there for billions of years, and they will remain for billions more, quiet and empty and full of lessons, waiting for anyone with the patience and the instruments to learn from them. And with that thought, we can let our minds rest, knowing that the emptiness is not frightening but instructive, not barren but meaningful, a reminder that even in the vastest silences, there is always something to discover. Let us imagine, then, a journey into this great emptiness, a voyage that would carry us far beyond the familiar lights of our own cosmic neighborhood and into the most profound darkness the universe has to offer. We shall travel in thought alone, drifting through the Boötes Void at whatever pace feels most comfortable, and there is no hurry at all. For time means very little when one is surrounded by distances so vast that even light requires millions of years to cross them. Picture yourself moving through this space, not with engines or sails or any mechanism we might recognize, but simply floating, carried along by gentle contemplation, watching the darkness unfold in every direction, and finding in that darkness a strange and unexpected peace. At the edges of the void, where we might begin our journey, there are still galaxies to be seen, though they grow fewer and more distant as we venture deeper into the emptiness. We are leaving behind the Hercules supercluster, that grand congregation of thousands of galaxies bound together by gravity and history, a structure so large that it would take us millions of years to cross even at the speed of light. And yet compared to the void we are entering, it is a mere village beside an ocean. The galaxies there are going about their quiet business, spinning slowly on their axes, forming new stars from ancient clouds of hydrogen, merging occasionally with smaller companions in collisions so gradual they might take 1 billion years to complete. We watch them recede into the distance behind us, their light growing fainter, their spiral arms and elliptical hazes blurring into single points. And then even those points begin to fade as we move deeper into the great nothing. The first 1,000,000 light-years pass, and still there is darkness ahead. We have grown accustomed in our imaginations to a universe populated with lights, where galaxies cluster together in families and those families gather into clans and those clans assemble into the vast superclusters that trace the bones of cosmic structure. But here there is none of that, only space itself, only the vacuum of the void stretching onward, and the faint whisper of the cosmic microwave background radiation that fills all of existence with its gentle warmth, just a few degrees above absolute zero, the echo of a much younger and much hotter universe. This radiation is our only companion for now. This ancient light that has been traveling since the universe was merely 380,000 years old, passing through voids and clusters alike without any preference, without any judgment, without any destination in mind. 10 million light-years into our journey, and we have passed the point where we might reasonably expect to encounter another galaxy in more ordinary regions of space. The Milky Way and Andromeda are separated by about 2.5 million light-years, which once seemed like an almost incomprehensible distance, and yet we have already traveled 4 times that far without seeing anything at all, without passing a single island of stars, without catching even the faintest glimmer of distant suns. The emptiness here is not hostile, though not cold in any emotional sense, but simply present, simply existing in its vast and patient way, asking nothing of us, offering nothing but space and silence and the opportunity to drift without interruption. 50 million light-years now, and we are approaching the center of the void, if a sphere so large can be said to have a center at all. On one side of us, impossibly far away but still detectable if we had instruments sensitive enough to catch their ancient light, lie the galaxies we left behind, the Hercules supercluster with its tens of thousands of stellar cities. On the other side, equally distant and equally faint, lies the Corona Borealis supercluster, another great gathering of galaxies that marks the far boundary of this emptiness. Between them stretches nothing, or very nearly nothing, 100 million light-years of space containing perhaps 60 galaxies where we might expect to find thousands upon thousands. Those 60 galaxies are scattered so sparsely through the void that we could travel for tens of millions of light-years without passing close to any of them. And we are doing exactly that now, drifting through the silence, watching the darkness ahead remain dark, watching the darkness behind us remain equally dark, finding in both directions the same patient emptiness. 100 million light-years, and we have crossed the void completely, emerging at last into the outskirts of the Corona Borealis supercluster, where galaxies begin to appear again like the first lights of a city seen from a long road across empty plains. We have traveled a distance that light itself requires 300 million years to cross, and yet in our contemplation we have made the journey in mere moments, which is one of the pleasant advantages of imaginary travel. Behind us now lies all that emptiness, all that silence, all that patient dark, and ahead of us lie galaxies beyond counting, structures that extend in every direction to the very edges of the observable universe. We have passed through the emptiest place in all of existence and emerged safely on the other side, carrying with us nothing but the memory of darkness and the curious peacefulness that comes from spending time in a place where nothing at all is happening. Consider now the light that is crossing that void at this very moment, photons that left galaxies on the far side 700 million years ago or more. When that light began its journey, when it first streamed away from young stars in distant galaxies and set out across the emptiness toward us, our own planet was a very different place. The great dinosaurs had not yet appeared, would not appear for another 200 million years or so, and the Earth was populated by creatures we would find strange and unfamiliar, early reptiles and amphibians, forests of ferns and primitive conifers, a world just beginning to recover from the vast extinction event that had ended the Permian period. All of human history, all of recorded civilization, all the generations of our ancestors stretching back to the very first organisms that might be called human, all of that has taken place in the time it takes light to travel a tiny fraction of the distance across this void. The photons that are arriving at our telescopes tonight left their home galaxies when Earth was young in ways we can barely comprehend, and they have been traveling ever since, patient and unhurried, crossing the great emptiness 1 second at a time, never slowing, never stopping, never wavering from their course. The void itself will not remain as it is forever, though on timescales we can barely imagine. It will grow even larger and even emptier. The universe is expanding, as we have known for nearly a century now, and that expansion is accelerating, driven by the mysterious influence we call dark energy, a force that pushes space itself apart, that increases the distance between all things not bound together by gravity. The galaxies at the edges of the Boötes Void are moving away from its center, and from each other, and the void is growing, slowly and imperceptibly on human timescales but steadily and inevitably on cosmic ones. The few galaxies scattered through its interior will drift farther apart. The darkness between them will deepen, and the emptiness that already defines this place will become more absolute with each passing billion years. In the very distant future, so far ahead that the numbers lose all meaning to human minds, the voids of the universe will merge together into a single infinite emptiness. All the galaxies will have retreated beyond each other's horizons, carried away by the expansion of space faster than light itself can travel, and each galaxy will find itself alone in a darkness that extends forever in all directions. There will be no Hercules supercluster visible then, no Corona Borealis supercluster, no cosmic web of filaments and walls, only individual galaxies drifting in isolation, their light unable to reach any observer beyond their own stars. This is the fate that awaits all things in such a universe. A gradual dispersal into the void, a slow fading into separation, a final and permanent solitude. It sounds lonely when described this way, and perhaps it would be, if there were anyone there to feel loneliness, but it is also so far in the future that we need not trouble ourselves with it now, need not let it disturb our rest or our peace. Need only acknowledge it as one of the many possibilities that the universe holds, one of the many endings written into the laws of physics, patient and unhurried, waiting in its own time. For now, though, we find ourselves in a much more fortunate position, living as we do in a galaxy-rich neighborhood where the lights are plentiful and the distances between islands of stars, while vast by any human standard, are small by cosmic ones. The Milky Way is surrounded by companion galaxies, more than 50 of them within a few million light-years, and beyond them lies the local group, and beyond that the Virgo supercluster, and beyond that the Laniakea supercluster, a structure containing perhaps 100,000 galaxies all moving together through space toward a gravitational attractor we have only recently begun to map. We are embedded in a web of light and matter, connected to the rest of the universe by invisible threads of gravity and the patient passage of photons, And we will remain so for billions of years yet. Plenty of time to observe and wonder and contemplate the nature of things. The Boötes Void is far away, 300 million light-years distant, and we observe it from safety, from comfort, from the gentle glow of our own galactic neighborhood, as one might observe a distant desert from the warmth of a well-lit room. There is something deeply reassuring in the fact that even emptiness has structure, that even the voids of the universe are not simply random absences but carefully shaped regions bounded by the filaments and walls of the cosmic web. The Boötes Void is not merely a place where galaxies happen not to be, but a feature of the universe with its own history and its own future, created by the same processes that created the great superclusters, shaped by the same gravity and the same dark matter and the same quantum fluctuations that rippled through the early universe billions of years ago. Nothing, it turns out, is quite as complicated as something, and the absence of matter in these great voids tells us just as much about the nature of the universe as the presence of matter in the clusters and filaments that surround them. Even nothing is something worth wondering about, worth contemplating, worth spending time with in the quiet hours before sleep. And so we return from our imaginary journey, drifting back through the darkness, passing once more through the great emptiness, watching the faint lights of distant superclusters grow brighter as we approach the edges of the void. The Corona Borealis supercluster fades behind us, the Hercules supercluster brightens ahead, and somewhere out there, still crossing the void in their slow and patient way, are the photons that left 700 million years ago, the ancient light that will arrive at our telescopes on some future night when we happen to look in the right direction at the right moment. That light carries with it the image of galaxies as they were in the deep past, a record of a universe we can never visit except through the patient accumulation of photons on our instruments, and it asks nothing of us except that we be here to receive it, that we pay attention, that we allow ourselves a moment of quiet wonder at the distances involved, at the time required, at the patient journey of light across the emptiest place in all of existence. The starlight crossing the void does not hurry. It has no reason to, no urgency, no destination except wherever it happens to end up, which may be our telescopes or may be the cold darkness between the stars or maybe nothing at all. It travels at exactly the same speed it has always traveled, 299,792 kilometers per second, neither faster nor slower, carrying with it the information of distant places and ancient times, patient and unhurried, crossing the great emptiness as if it had all the time in the universe, which of course it does. And there is something deeply peaceful in that thought, in the image of light moving through the void, in the knowledge that even now, at this very moment, photons are making their way across that 300 million light-year darkness, carrying their messages from one side of the emptiness to the other, asking nothing, expecting nothing, simply traveling, simply existing, simply being light in the way that light has always been, patient and unhurried, crossing the void.